In this video, we're going to talk about how both equilibrium and free energy are related to voltaic cells, and we're also going to talk a little bit about reference electrodes and what they are. So earlier in the semester, we were talking about thermodynamics and delta G, which is free energy, or the amount of free energy available to do useful work. So if we take that logic and apply it to electrochemical cells, it makes sense that if we want to do electrical work or electrochemical work, then that would also be directly related to the amount of free energy available to do useful work. So the delta G of an electrochemical cell is going to be equal to the work done by an electrochemical cell. And we can calculate the work that is done by electrochemical cells using this equation here. So N is the number of electrons transferred in a redox reaction, or a reaction that is taking place during an electrochemical reaction or in an electrochemical cell. F is Faraday's constant that has units of 96,500 coulombs per mole of electron, and E cell is the voltage that is produced by a particular electrochemical cell. Now, since delta G equals the electrical work, we can rewrite the equation as delta G cell equals minus N times F times E cell. So let's do a quick calculation to determine how much work would be done on this particular reaction taking place in a voltaic cell that produces 2.71 volts. So we know we're going to use this equation here, delta G equals minus NF E cell. We're given E cell here, 2.71 volts. We know what Faraday's constant is, 96,500 coulombs per mole of electrons, and the only thing we really have to figure out is what N is. So how do we figure out how many electrons are transferred in this reaction? Well, for this particular reaction, it's fairly simple because you can look at the products and the reactants and notice that we have two ions. We have a copper 2+ ion and a magnesium 2+ ion. And also remember that when we're talking about redox reactions, we can split an overall reaction up into two half reactions. So we can split this reaction up into a magnesium half reaction and a copper half reaction, and then we can add electrons to whatever side is necessary in order to balance the charge. So if we were to write a copper reaction, we could write copper 2+, and that's going to make copper solid. And in order to balance the charge, we would have to add 2 electrons to the reactant side. Now we could do the same thing with the magnesium. We can write it just as we see it in the reaction above. We can have magnesium solid, and that's going to produce magnesium 2+. And again, to balance the charge, we could add 2 electrons to that. So you can see in both reactions we have 2 electrons, so that means that 2 electrons were transferred during this particular reaction. So now we have everything we need to solve this problem. Delta G of the cell is going to be minus 2 moles of electrons times 96,500 coulombs per mole of electrons times 2.71 volts. And if you look on your worksheet, you will notice that a volt equals a joule per coulomb. So what we're going to get out of this is units of joules, which is exactly what we want for delta G. So delta G cell is going to equal minus 523,030 joules. We can put that into kilojoules as minus 523 kilojoules. Okay, so that's going to be delta G, and that's also going to be the amount of work that is done on this circuit. Right? And we know that since delta G is negative, that this is a spontaneous reaction. And one thing about voltaic cells is that they are always spontaneous, right? Meaning that if you were to hook these up, so you have a magnesium half reaction and a copper half reaction, you hook them up together with the salt bridge and a wire that connects the 2 electrodes, then this reaction will spontaneously occur and produce a voltage of 2.71 volts. So I want to step back a little bit and talk about the standard reduction potential that we talked about in the last video. That's going to be a half reaction. So the question becomes, how do we measure this? How do we get the voltage of a half reaction if it isn't even a full reaction? If we can't just have fluorine gas and have it make fluoride ions, because that's not a full reaction. So how do we measure this 2.890 volts or the 2.075 volts or anything else in this table? Well, the answer is that all of these reactions or these standard reduction potentials were measured in reference to another electrode, and that is called the standard hydrogen electrode, or the SHE. And the reaction of the SHE is shown right here. And the reason it's called the standard hydrogen electrode is, well, number one, it uses hydrogen gas. And it's standard because it's under standard state conditions. So the gas is at 1 atmosphere pressure, and the concentration of acid is 1 molar. So you can consider this particular electrode, as it's shown here, as one of the half reactions, right? Again, this is only a half reaction too because we have electrons there. So this wire up here is going to have to be connected to another half cell, right? Some electrochemical cell over here, and there's going to have to be a salt bridge that connects those together. So over here, this particular half cell is going to be the one that we're interested in. So it could be the copper half reaction, it could be the zinc half reaction, it could be the fluorine half reaction. And since we define the voltage of the standard hydrogen electrode to be 0 volts, the voltage that we get from hooking these half cells up together is going to be related to the voltage of the particular half cell that we're interested in. So here's a better picture of what it would look like to hook up a standard hydrogen electrode to another half reaction and use that to determine what the voltage of the particular half reaction is. So here in this case we have the standard hydrogen electrode on the right, and we have the zinc half reaction on the left. So in this case, when we hook these up, we're looking for a positive voltage. And again, the reason that we're looking for a positive voltage is because this is going to be a spontaneous reaction, so we know the voltage overall is going to be positive. Okay, so in order to get a positive voltage, in this case we have zinc as the anode and the standard hydrogen electrode as the cathode. So the equation that we're going to use to figure the voltage of the cell is as follows. We have E cell, and E cell with the little naught here, the little 0, refers to standard state conditions, and that's going to equal the standard reduction potential of the cathode minus the standard reduction potential of the anode. So in this case, we know what the overall voltage is. We know E cell being 0.762 volts. So here we are right here, 0.762 volts. And we're trying to figure out what the voltage of the zinc half reaction is, this one right here. So we know what the overall potential is. We've defined the standard hydrogen electrode to be 0 volts. So all we have to do now is solve for the zinc half reaction, and we end up getting minus 0.762 volts. Now we can do the same thing with the copper half reaction, except in this case, the standard hydrogen electrode ends up being the anode, whereas the copper ends up being the cathode. So we'll use the same equation we used before. We know the overall voltage from hooking this up, right? So we get 0.342 volts. We're trying to figure out what the voltage of the copper half reaction is. We know what the voltage of the standard hydrogen electrode is at 0 volts. So if we solve this equation, we end up getting a standard reduction potential for copper as 0.342 volts. So we can use the same process or the same equation that we used in the previous example to determine the voltage of any voltaic cell, right? So we can use E cell equals cathode minus E anode for any two half reactions in a voltaic cell. So in this case, we have iron 3 plus going to iron 2 plus and iodide going to I2. So I've given you the standard reduction potentials for each of these half reactions. So in order to figure this out, we would just use this equation again and fill in both the cathode and the anode. But the question here becomes, how do we know which of these two half reactions is the cathode and which one is the anode? Well, the simple answer is the one that is the most positive is the cathode. The one that is the most negative is the anode. So in this case, the most positive one is iron, 0.770 volts. That's the cathode. So the other one is going to be the anode. So we'll have E cell equals the E of the cathode, 0.770 volts, minus 0.536 volts for the anode. And that's going to equal 0.234 volts. Now you know if you've done this right, if you get a positive number. If you get a negative number, then you've done it backwards. Okay, so remember again, these reactions from a voltaic cell are going to be positive, and that means that it's a spontaneous reaction. So up until now, we've talked about how different components of a voltaic cell can result in different voltages. So if we have a standard hydrogen electrode and zinc, it gives us a different voltage than the standard hydrogen electrode with copper, and that gives us a different voltage than if we put copper and zinc together. But everything we've done so far has also just been at standard state conditions. But consider the reaction that's happening. So we have electrons being transferred from anode to cathode, and if electrons are being transferred, something is happening. There's a reaction going on, so something has to be changing, right? We have to have differences in concentrations. The concentrations of the solutions have to be changing over time. So if you recall back to the previous video, we looked at the copper-zinc voltaic cell, and we noticed that over time, the zinc electrode loses mass, whereas the copper electrode increases in mass. So what's going on here? Well, we figured that since electrons are moving from anode to cathode, then the zinc that's on the electrode itself must be losing electrons and dissolving in solution. So it's going from zinc solid, right, zinc solid to zinc 2+. So that would suggest that the concentration of zinc 2+ in this case is increasing over time. Whereas on the other side, electrons are building up on the copper electrode, so that means the copper 2+ must be grabbing onto those electrons and turning into a copper solid, and that's also shown in the overall reaction here, copper 2+ going to copper solid. So since we're losing copper 2+, the concentration of that must be decreasing. So how do we figure out how the voltage is going to change based on differing concentrations? So the previous equation that we use, E cell equals E cathode minus E anode, that was for standard state conditions. But if we want to correct for non-standard state conditions, we have to use the Nernst equation, which is shown here in two forms. The first form is for any temperature, and the second form of the equation is for temperatures of 298 Kelvin or 25 degrees Celsius. And if we go back a couple chapters, we should remember Q is the reaction quotient, and Q equals the concentration of products over the concentration of reactants. Okay, so that's showing you that the concentration ratio of the products to the reactants is going to change this part of the equation here, and that's like a correction factor for the voltage of the cell. So the voltage of the cell at non-standard state conditions is going to equal whatever it would be at standard state conditions minus whatever this correction factor is. And that's going to be determined based on how the concentrations are changing or what the concentrations of each of the components are at a given point in time. So let's go through an example. And I will say that this is a very difficult example because you really have to understand what's going on. So hopefully by doing this and understanding this example, you'll be able to easily do the ones that are on the worksheet. So consider a cell starting at standard state conditions. So we have the copper and zinc voltaic cell, one that we've seen before, and we're asked to determine the potential after the reaction has proceeded enough for zinc to have changed by 0.35 moles per liter at 25 degrees Celsius. So the first thing we have to consider is, where does this reaction start? We're not giving specific concentrations of the copper and the zinc, but we are given another clue to tell us what the concentrations were initially. Because all we know is that we're trying to figure out what happens when the zinc 2+ changes by 0.35 moles per liter, but to do that we got to know where our starting conditions are. Now luckily we're given a clue here in the question, and that we start at standard state conditions. So if we start at standard state conditions, we should know that the concentrations of both copper 2+ and zinc 2+ are going to be 1 molar. Alright, so that's the first step. Now the second step is to determine which way the reaction is going. We know that the zinc is going to change by 0.35 moles per liter, but is that going to increase in concentration or is that going to decrease in concentration? So just as we talked about a few minutes ago, remember that we have zinc solid turning into zinc 2+, and we have copper 2+ going to copper solid. We can also see that in our chemical reaction, right? We have copper 2+ going to copper solid, and we have zinc solid going to zinc 2+. So that tells us that the concentration of zinc 2+ is going to be increasing by 0.35 moles per liter, and the concentration of copper must be decreasing by 0.35 moles per liter. So now we know that the concentration of zinc 2+ is going to be 1.35 molar, and the concentration of copper 2+ is going to be 0.65 molar. Okay, so we've done most of the stuff that requires the thinking. So now let's just write out the Nernst equation and determine what we need to figure out the voltage of this particular cell. So we need the standard cell potential. We know how to do that. We've done that before. We need to figure out how many electrons are transferred in the reaction, and we need to figure out Q. We've already mostly figured out Q because we have the concentrations of our products and reactants. We just have to figure out which one's a product, which one's a reactant. So we'll get back to Q in a minute. So the first thing we're going to do is to figure out what this is, the standard cell potential. And to do that, we'll just use this equation, same one we used in previous slides. So we can look up the standard reduction potentials for copper and for zinc in the appendix of your textbook, or you can just look back at previous slides to see that copper is 0.342 volts, zinc is minus 0.61 volts, and if we solve for the standard potential of the cell, we're going to get 1.104 volts. Again, we know that's right because it's a positive number. So now we have our standard cell potential. Now let's try and figure out N, how many electrons are transferred in this particular reaction. So as we did in a previous example, we can write out two half reactions. So copper 2 plus 2 electrons producing copper solid, and zinc 2 plus 2 electrons producing zinc solid. Right? Remember, we have two 2 plus ions, and those 2 pluses have to be balanced by 2 electrons in each of the reactions. So that means that we have 2 electrons that are transferred in this particular reaction, so N equals 2. Okay, so now our last step is to just put it all together to figure out the cell potential at non-standard state conditions. We have the cell potential at standard state conditions, minus 0.0592 volts over 2 moles of electrons, and we have our products over our reactants. And how do we determine which is products and which is reactants? Let's quickly go back up to our reaction. We have zinc 2 plus as a product, copper 2 plus as a reactant, and remember when we're doing these equilibrium calculations, whether it's K's or Q's, solids are not included in the equilibrium expression, so we don't have to worry about copper solid and zinc solid. So we have our products as zinc, over the reactants as copper, and when we solve that, we end up getting a voltage of 1.043 volts. Now notice that these two voltages here are not all that different. This one here, the 1.104 volts, was for standard state conditions, and the one below here, 1.043 volts, was for non-standard state conditions. So the concentration of zinc and copper changed by quite a bit, right? Somewhere around 35%, but the voltage didn't change all that much. And this is how batteries work, because what we're really looking at here is turning chemical energy into electrical energy, which is a battery. So an example of a battery is something that you have in your car, so a lead acid battery, and the reaction is there above. We have the lead and we have the acid, okay, lead acid battery. And this particular reaction has a voltage of about 2 volts. So in the battery in your car, it's a 12-volt battery, and that's because 6 of these cells are hooked together in series. So remember, as we're doing this example in the previous slide, we saw that we changed the concentration of copper and zinc by quite a large amount, but the voltage didn't change all that much. So the same is for the discharge of the lead acid battery or any battery. Okay, so we start off at a full voltage, okay, in this case for one of the cells, somewhere around 2 volts. But you notice that even after about 90% of the battery has been discharged, we haven't lost a lot of power, right? We haven't lost a lot of voltage there. It's not until the last little bit that it really starts to tank. And this doesn't quite go down to 0, but eventually it would just go down to 0. So as concentrations decrease from 1 molar to 0.1 molar, so that's a factor of 10, the voltage only changes by a very small amount, from 2.04 volts to 1.98 volts. So in a way, it's kind of like a buffer, right? So remember when we were talking about buffers, if we add some acid or base to a buffer, the pH doesn't change all that much, even though we've added a good amount of acid or base. So this is a similar type of situation where concentrations of reactants and products are changing by a decent amount, but the voltage is not changing all that much. So now what does it mean when a battery or a voltaic cell is showing 0 volts? Basically, when the battery is dead, what does that mean chemically is happening? So what it means is that the battery has reached equilibrium. And remember, at equilibrium, reactions are still proceeding in the forward and reverse direction. There is just no net change in the concentrations of products and reactants, right? The concentrations of products and reactants remain constant. So if there's no net change, there's no electrical energy available to do any useful work, because any electrons that are flowing one way will be counteracted by electrons flowing the other way. So in this case, we've reached equilibrium, right? So a dead battery means the battery is at equilibrium, and there's no more energy available to do work, right? So here we go, equilibrium, E cell equals 0, and equilibrium, Q equals K. So from the Nernst equation, if we substitute Q for K and E cell to be 0, we can rearrange the equation to get this guy here, and we can figure out the equilibrium constant of a particular battery. So let's just do a quick example. If we want to calculate the equilibrium constant from a standard cell potential for this particular reaction, and again, I've given you the standard reduction potentials of the iron and the lead half reactions. So we know we're going to use this equation here, and we're going to try and figure out what K is. So what do we need? We need N, number of electrons transferred. We need the standard cell potential. And we've done standard cell potential before, so we can do that first. E cell equals E cathode minus E anode. And just like in the previous example, we have to determine which one is the anode, which one's the cathode. Remember, the cathode is the one that's the most positive, anode is the one that's most negative. In this case, both of them are negative, but the one that is the most positive is the lead. So that's going to be the cathode. So we're going to have negative 0.126 minus 0.447 volts. And that's going to equal 0.321 volts. Again, we have a positive number, so we know we did the right way. So now we have to figure out the number of electrons transferred. And just like the other examples, this one's fairly simple. We could write out the half reactions. We have a lead 2+ and an iron 2+. Since they're both 2+, we know we'll need to add 2 electrons to each side. So the number of electrons transferred is going to be 2. So if we solve this equation, what we end up with is log K is going to equal 10.84. 10.84. That's log K. We have to figure out what K is, so we have to take the inverse log of that number. Right? So that's going to be 10 to the power of 10.84, and that's going to equal 6.99 times 10 to the 10. So a really, really big equilibrium constant, and that's what you're going to see with these types of voltaic cells. Equilibrium constants that are very large because they are very, very product favored. So before I end off this chapter, I want to give you a couple of examples of how to determine the number of electrons transferred in an electrochemical reaction. So all the examples that we did in this chapter were with 2 electrons, right? We had a copper 2+ and a zinc 2+. Each of them had 2 electrons in each half reaction, so the number of electrons transferred in those was 2. So what if you have an example like the ones shown below here? So the first example, silver plus 1 electron, producing silver solid. Second one, chromium 3+ plus 3 electrons, producing chromium solid. So what you have to do to determine how many electrons are transferred is to balance the reactions in each of the half cells. So the first one's not too bad. We have 3 electrons transferred in the chromium reaction, 1 electron transferred in the silver reaction. So in order to balance the reactions, or to balance the electrons, we would simply multiply the silver reaction by 3. So now each of the reactions has 3 electrons, and the electrons would therefore cancel out. And then we can say that 3 electrons were transferred in that particular reaction if we were to write this as an overall reaction. Now for the next example, nickel 2+ plus 2 electrons and chromium 3+ plus 3 electrons, the same strategy applies. We have to balance the electrons. We have to make them equal in both of the half reactions. So in order to do that, we would multiply the nickel reaction by 3 and the chromium reaction by 2. So now we have 6 electrons in each of those half reactions. So if we were to write an overall reaction, we would say that 6 electrons were transferred. Right? So when you're calculating N for the Nernst equation, make sure that the electrons are equal with each half reaction, and that's going to tell you how many electrons are transferred. All right, so that's all I have for this section. If you have any questions, please let me know.